a delay. Technology catches us. All right, so I just want to talk a little bit about the education and workforce development programs that we've been doing with QSEC. This is going to be sort of the whirlwind tour through some of the things that we've been doing. Nancy Holenchick's on this slide. She's been sort of my primary collaborator on all this, but there are quite a few other people, and you'll see some of their names as we go who have also been involved. Well, this is K-12 and undergraduate. There's also a little piece of graduate, although I won't talk so much about that here. But one of the driving ideas for what we have been doing is the need for sort of equity and access that's combined with what's currently really a lack of knowledge, and to some extent, as I'll note in a minute, sort of a fear or uncertainty about what this whole quantum thing is, right? That means we really need more education, and I'll argue that we need it within formal education settings. There's plenty of interesting things, and some of the stuff we're doing is also in informal settings, so I will contradict myself a little bit there as well. But the idea being, especially at K-12, that need to get it in the classroom so all students actually see this. All right, so this part of this started with a survey that we have done to understand what undergraduate STEM students know about quantum and careers in quantum and what their interest is in it. So we said, all right, we're going to survey Mason students and find out what they know. One of the questions on that is, was literally that, what do you know about quantum careers? And just nothing, a little bit, some, quite a lot. And are you interested? I'm interested in pursuing it. And to disagree, to strongly agree. What you can see is that more than half said they know absolutely nothing. And these are STEM students, undergraduate STEM students at Mason. Another 30% said a little bit. So, 87% knew little or nothing about it. But there are sort of 60-odd% who are like, kind of interesting, right? So that's where I think really the big summary of where a lot of STEM undergraduates are right now. And when we actually went back and interviewed some of these students. And I thought this was sort of pretty typical that I only know a little bit the physics definition of quantum, but I want to learn more about it, right? So there's sort of an interest in this, if not a knowledge. The other thing we found as we looked through these data, and this was 180-odd students, so a pretty decent sample, is that if you break it down by male and female students, sort of men and women, you've got this, you sort of see a little bit more skew towards interest among our male respondents to this. But it turns out that if you divide it up, we also divide it up by the area of their major, right? With the life sciences there in red, sort of computer and cyber, and this is sort of broad lumpings of these things, physical science, engineering, and math in the green. Right, there were also differences by major. So our life sciences students were very much like, not so interested, which is also interesting and useful as we think about some of these application areas, which have come up a number of times today and in other days, right? Some of these students may actually be important to some of those medical applications ultimately. But also maybe not as much of a surprise. This is a physics-y thing, and those students went into some of those life sciences probably not wanting to do physics. And so it turns out that those gender differences disappear when we just focus on our computer, physical science, and engineering and math majors, the ones that we sort of have more direct connections with in the quantum right now. So what that tells me, at least to some degree, especially as we look at the distribution of students within these majors, is if we want to build a diverse quantum workforce, we're going to have to do something a little bit different, right? We know our physics students or computer science students are interested, and that's great, but those are the majors which are struggling the most for diversity right now anyway. So that's not going to solve our problem. right? So we have to think differently. We have to think more broadly as we expand on this. Yes. So in this case, I'm talking about race and gender. Yeah, so the number of women, the number of underrepresented minorities in STEM, those groups. But it is also ultimately, so it relates back to when we talk about discipline, right? We're currently drawing from sort of the yellow and green. And so we'll have to think about, I think, and one of my arguments is we have to think about what we do with those who are in those red bars with our life sciences students and how we get them interested and thinking about where this fits more broadly in their education.
So just a follow-up, like, the research is interested in involving the life sciences student is what
Well, this is a survey. I mean, so we were trying to understand broadly what STEM undergraduates know and what their interests are. And this is just one of those things that sort of came out of it. That said, I'll tell you, my interest in it is twofold. One is this question of diversity within quantum. If we want to address that, currently, the physics and computer science and those sort of disciplines don't have it. We're not very good at it, right? We've done a terrible job historically, and we've got to think about how we do that. And that's also other things that we're working on. Some of the stuff Laura's working on from a different angle is how do we address it even within those disciplines, which is really important. But there's this pool of students in life sciences, which tends to be more diverse, for whom there are impacts of quantum, right? Quantum computing as it's applied to drug discovery, quantum sensing as it's applied to measurement of all sorts of health conditions, right? So there are actually connections here that could provide us a way to think about engaging with those students and those populations as we try to grow the field. That's maybe the point, yeah.
Oh, I want to ask, what is that science?
So in there, that was biology, it was forensic science, trying to remember who else we had in there. Those were sort of the main ones that I remember. There might have been a couple of handful of psychology students, but again, it was, we sort of broadly put this up and asked undergraduate students to fill out the survey and then sort of bin where their majors were. So, but I think most of those are biology majors.
This is Mason, right?
This is at Mason. So we're actually thinking about whether we can do this across other institutions and see, you know, are there differences? But this just got accepted for publication the other day. So it is now actually out there. And okay, so I had said, right, as we do this, and one of the things that students actually, when we interviewed them, pointed out is we need this earlier. We talked to these undergraduates, they said, this is great. We need to be learning about this sooner. And as I said, right, we want it to be in classrooms and not just physics. Most students do not take physics in high school. So if we want them to be seeing this, it's got to be in math or connections in chemistry or in other places, or most students aren't going to see it. It can be used just as also as an approach of understanding science. How do we understand how the world works, especially the world we can't see, right? Will it be relevant to careers in the future, right? Teachers are very interested in thinking about and getting students to think about what those career options are. So connecting it to that makes sense. And then, you know, ultimately, I think thinking about standards are going to be important, administrators, some of the materials. But in sort of this vein, we started a program been calling Quantum in Your Classroom. We've run 6 sessions sort of over the last year plus at this point. We have another one coming up this weekend. 5 in-person sessions which were 5 hours. So it's sort of like an all-day Saturday kind of thing with teachers. We did one virtual 2-hour one, 73 teachers. This was by far the largest of this. So a lot of those were in that one. And then we had 5 teachers that worked for an extended time last summer to kind of really think about curriculum and development a little bit more than we had. This is actually the distribution and not what we expected when we started this. When we started this, we expected by and large, we would have high school teachers, but we didn't restrict it. We just sort of said, okay, we're going to announce this out there. We're going to connect with teachers as best we can and sort of see who shows up. Turns out we're sort of, 40% is high school, 40% elementary, and about 16% middle. Of course, the middle is smaller, mostly because that's fewer years of school, right? So we had almost as many elementary school teachers as we had high school teachers. Not at all what I would have told you when I started, just to give you the demographics. It pretty well matches actually teacher demographics, if not STEM demographics. And one of the things that I found very interesting in doing this is that it is the earlier grade teachers who, in some ways, are more flexible. And in terms of thinking about how to bring quantum in. All the teachers are so tied to their standards of learning, to their tests that they have to give at the end of the year, that it's very hard in, say, a chemistry class or a math class to add anything, physics. There's often if it's AP, it's at the end of the year, right? So those teachers do some of it. And that was the rest of the demographics. But the elementary teachers, again, have a little more flexibility. How do we bring this in and relate it to measurement and talk about why quantum, looks a little bit different, or, science and the nature of science. And some of these topics are coming up. Exponential growth. There's an exercise that we've been using that was developed out of Chicago for fairly young ages that connects to quantum computing exponential growth. It's really just about understanding exponential systems, right? And how things scale, which is really useful. And then there's just a blurb on why that's related and why quantum computing poses this possibility of exponential growth. They're not getting a deep understanding of quantum computing, but hearing some of the words and terminology and connections. To point out also, one of the exercises we always do with these teachers is to start with, why do this? And not to tell them why to do this, but actually what we want to do is what are they thinking? They showed up to this workshop. Why? Why show up to a workshop in quantum if you're an elementary school teacher? This is not obvious, right? It was certainly not obvious to me. So, they made a whole bunch of cards out of these things, but it's things like it may provide our youth with more and better career opportunities, where innovative technologies will increase student engagement because they're inherently fun. Political and cultural participation are increasingly shaped by computing, and students need to understand the impacts of tech. It helps students understand scientific knowledge, how scientific knowledge evolves over time. Technology innovation helps humanity flourish. The next generation needs to be able to do all of that. And so not all technology is good for society. Students will need to be able to think critically about technology and the ethical issues that arise from it. So the different colors are actually different aspects of this. Everything from sort of this personal agency, this is kind of cool side of things, economic and workforce development, competencies and literacies, right? They need to know it. School reform and improvement, this equity and social justice lens, citizenship, and technology. And teachers pick all of the above, right? When they pick sort of what are their reasons, they really span this range. It's not just one thing, which also tells us that we have to think about these different implications as we bring it into the schools. I'll also point out that, right, at elementary school, they're often really focused on this equity and access issue. We want to make sure all students understand this. A lot of them have been working in schools that are have low-income students and some second language learners and various things, and they're thinking about those students. Found it really interesting. A couple of them said, well, I'm working with second language, English language learners, and this puts them all on basically the same footing because nobody knows what you're talking about to start, right? So it was, again, that when you're talking about middle and high school, they're also talking about equity, but they start really thinking more about the content, right? Which makes sense. That's where that content piece becomes important. Some of the quotes from the teachers, I'll put these up so that you can look at them. But right, they're looking at giving students a leg up. Here's the, on the bottom left, the quote about English learners, right? And also this idea that it's totally untraditional. So this is something new, something cool to kind of put in. This is not the way they've taught this material or thought about it before. And just, so this is some of our teachers, just to kind of get out the kinds of things that we do with them, right? What is the distinction between classical and quantum? Sort of the key topics, like at a very, and this is, right, we've got 5 hours. They're not walking away with deep understandings of these things. It's some of the vocabulary, a little bit of connection to physical systems. What is a quantum state, superposition, entanglement, measurement, right? What do these things even mean? We use polarizers in all of these as a quantum effect, show them what happens when you put 3 polarizers together. Is always a really nice way to illustrate and talk about this. We like to talk about the applications, right? Computing, cryptography, those kinds of things, so that they have a sense of why. Where is this all going? Why are we talking about this now? And we've developed this quantum chutes and ladders. Some of you played this last year for this, and we have the teachers play it, partially because then they're using that terminology and describing it with respect to these systems and how that works. And then these small activities. So this Epic C stuff is the activities out of Chicago for younger ages. So basically they break up into groups and they each do one. We also use some of the Waterloo activities as well that they've developed. Those mostly we steer our like high school physics and CS teachers towards, and everybody else away from them. They're really good, but they're at a much higher level. You wouldn't want elementary school teachers working on those, whereas these are really good for the elementary school teachers. So again, over the summer last year, we did some curriculum development, really trying to think about some stuff we put in their hands at these workshops, but there's just not that much stuff available at this point. How do we build it? Just trying to get them to help us start thinking about what can you develop for these grade levels and what are the resources. So some of the barriers and concerns that have come out from the teachers, it's unclear how this stuff is connected to standards. There's not that many resources at this point. They're not always sure the students have the background knowledge they need. One of the things that really came out clearly is that the length and format of these workshops has a huge impact on how teachers leave in terms of their thinking about it. Our 2-hour online, which was really very much an experiment, was a disaster in this way. Disaster, probably a little bit strong, but they did not come out with a lot of comfort and feeling like they could go in the classroom and do this stuff, which probably shouldn't be a surprise, right? Whereas those who are with us in person for 5 hours were like, yeah, these little activities that we did, I could take that to my classroom. I could do it and talk about it. So yeah, the ones that were concerned about the content and their knowledge, and these guys were almost all in that virtual session. So that, yeah, they don't necessarily feel comfortable talking about it, but they also see a lot of opportunities, right? The connections to a lot of study areas, some of the math areas, some of this measurement stuff, the impacts on students' careers, the nature of science, right? So, allowing kids to think out of the box, it's going to blow their minds and spark their interest, right? This is what we want to do. There's some really cool things about quantum. So next steps, as I said, we're continuing to have a few of these workshops and think about all of these things. And I'll point, this is really the major next step, is that Nancy Holenchek is PI on a project, just we're calling Quantum is Elementary. Since this was actually such a hit with elementary teachers, we are focusing on that. And so we had put in a proposal. She really had put in the proposal, led it to do this with elementary elementary school teachers at a bigger scale. And they came back and said, well, that sounds great, but we're not sure you can do it, which is fair. So they gave us an eager, which is a short-term, like proof of concept kind of project. So we've got a couple of years to pull them in, and we've started meeting with the elementary school teachers and try to gauge sort of where they're at and what they're thinking about all of this. So that's the teacher pieces of all of that. And I should say Nancy's going to talk more about that project tomorrow. So I'm going to leave that for her to do. We've also been working with high school students. So these are rising seniors. We're gearing up to do this again this summer. We've run it twice before, 13 students in 2022, 24 last summer. We've done 2 weeks virtual of like, what is quantum and how does it all work? And then 1 week of this sort of immersive in-person experience. The first year we bust them all around this region, which was terrible. Last year they were on campus, terrible in a totally different way, but much better, really much better logistically, other than worrying about the fact that you have 24 teenagers on campus that you have to watch out for. But when we did it, right, so, well, this is the demographics of the group. So we've really gotten a very diverse group from all of the large school districts in the region. This is kind of the rough, I mean, it's a lot of the same pieces of topics that we've been doing for the other projects as well. And then, and this is sort of the very tiny font, which I don't expect you to read, but mostly see there was a very busy week when they were on campus. We went to we saw all the labs at Mason, we went to MITRE, we went to Maryland, we went to NASA, they got to go to the White House, which was really cool, meet with the Quantum Coordination Office. So all sorts of stuff, really packed schedule. Here they all are at the various places. And it really did, I think, impact sort of these students thinking about quantum, right? If it wasn't for this program, I wouldn't see myself getting interested until at least the time I was in college. You know, and this one, again, back to that life sciences thing, we had a couple of kids who were thinking more medicine in terms of what they ultimately wanted to do. These are high school kids, so they have no idea at that point, but they're like, oh, maybe these things actually connect. They loved going to Rob Cressman's lab and seeing some of the quantum sensing stuff he's doing and hearing people talk about this, just generally deepening their interest in STEM, which is a lot of the goal. And this was a student who had really been thinking more IT and was now thinking, oh, maybe quantum cryptography would be interesting. And so after that, we gave them all the option to present posters. Some of you have heard in, well, certainly in the last discussion and earlier discussion of the Quantum World Congress. So our students came and presented posters. We basically gave a program. We said, you know, what is quantum going to do in the future? And, you know, put together, do your own research and kind of think about what that might look like. And they put together posters. And all of the industry people who saw them were really impressed with what high school students could do. And I'll say, other than sort of touching up issues, I think you looked at a lot of them, didn't you, John? Were you helping? You were helping us with some of these posters. They did a really good job at sort of scoping out what all this is. They got to get up on stage and talk about their experience. So really great experience for them. We also offered some micro internships, which we hope to do again this year, of a few weeks of getting involved, most of them at Mason. We also collaborated with INA Solutions, which is a small business in Fairfax that does a mix of quantum machine learning types of stuff. I think this year we've got a few more lined up outside of Mason in industry for this. So, you know, we're working to figure out how to sustain these programs. But let me go, and I'm just going to touch on one more thing before we're done, which is something we've sort of been starting up a little bit more recently, which we're calling the Quantum Pathways program. And it's really a pilot at this point, but this comes from this idea that if you look at the distribution of institutions that are offering quantum courses, right? Most of them are at our doctoral granting institutions, right? Large research institutions is where almost all of these are. So most masters, primarily undergraduate, minority serving institutions types of places, 2-year colleges, right, don't offer quantum in any form. And again, thinking about this workforce that we need to grow, we need to build, and we also need to think about the diversity of the fact that those places don't have any of these courses and the students therefore don't know even what this opportunity is, could be a problem. So we've started to create these workshops for students, again, to just introduce these ideas. What is it? What are people doing with the kinds of things we've been talking about before? It's generally also included a panel discussion of people who are actually doing this in industry. So they get to see that. We've done 2 so far. One was really, we were focused on community college. We also got a couple of Howard students. Then we did the most recent one, which was just last Friday at Bowie State with Wei Wen Zhang, who also joined us, where we pulled them in. We have one planned for Howard in another month or so. And just a comment that, you know, I don't know, this was a mechanical engineering associate student. I was like, I don't know what I can do with it, but maybe I can, right? This connection, I sort of get that idea going that maybe I should think about where we go next and how I connect to what my next steps are beyond my 2-year degree. So with that, I just want to leave you with the idea that students are really excited to learn about this. I mean, and this is, you know, really K to 20, right? But there's still a lot of gap in knowledge in terms of what this all is, whether that be at K-12, even at Mason for STEM undergraduates broadly, right, to sort of other institutions that have even less access than we have here. So thinking about how we address that, how we start with this process of getting students to understand what it is so that then they can go into the more advanced courses, they can actually start really preparing themselves to do this work in the future. What we're aiming at and really providing those on-ramps for students. So, thank you. Questions?
Well, the net tips,
Mhm.
So, is there any correlation that if the content were provided in native language, they would have perhaps more than the English language? Is there any kind of correlation between that?
So I am far from an expert on this. That is not my, but what I will go back to that quote because I think it was relevant and just point out there. So, right, this comment, it's sort of 2 ways. One is, I mean, there was a comment earlier, I think it's actually on the previous slide, which is we need materials in the native languages. So I mean, I think that certainly helps, right? If you have to both understand the language and the content, it's harder. But this is also, I think, pointing at this idea that here's a concept that someone who speaks English doesn't understand either, right? So everybody's sort of starting at that same level. There's a lot of language that you're learning just as to what these concepts mean. You know, what does it mean to be in superposition? If you're an elementary school kid, that's not a word, you know, so someone who's just learning English as well as an English speaker is trying to figure out what that means too. So there's also this equalization even in English, but I think there was also the point made that we also need access to other materials in other languages. So with our teachers, we've been trying where we can. There are a handful very small handful of books for Spanish speakers, right? There, but of course, more broadly in more languages and all, you know, none of that exists at this point.
Everything goes down to the English kind of literature, right?
Sure.
So like at some point, kids have to translate from their native language to the English. So which kind of like methodology is better, like teaching kids in the native language or try to teach kids in the English from the main video?
Yeah. I know, Laura, you may know as much about this as I do, having been in K-12 teaching.
I mean, I think it's pretty obvious that if you offer bilingual options, then the students will better, less truancy, all of these things, just version out of bilingual options. I imagine though, for things like quantum, like Dr. Rosenberg saying that it does kind of, I had much more success as a physics teacher with specifically Hispanic students because it's just math. And a lot of it was because there was like, smaller words, I don't know, biology. So I do think this is a very good opportunity, without the bilingual.
Yeah, and I think part of what schools do, right, is the more you can do both, right? They're building their language skills just by being in an English-speaking school, but where you can provide those materials in their native language, it helps because then they're not missing as much stuff. So you kind of have to do some of each, I think. But again, I am not a bilingual teaching expert in any sense. This is mostly coming from the teachers who are, right? They're in the classroom. So it's what we're hearing as the things they need. They need more of those materials in other languages, but they're also seeing opportunities in this, yeah, independent. So yeah.
From your teaching experience, do you prefer to teach elementary students or university students? Which one do you prefer?
So I always said prior to starting on this project that I would never do K-12. That was not, I am a sort of university, working in higher ed is sort of where I'm at. This has been a great experience. I will say Nancy Holenchek is very much the expert at the K-12 side of things. I have learned a ton about working with teachers and working with K-12 students, and it's been a lot of fun. I think my heart is still in higher ed and understanding what we do there and how that all works. But I'm sort of doing both now, and that's great. So, but yeah, no, historically, I've done much more of my work thinking about higher ed and where we are. It just happened we got this funding, which was ended up being really focused on K-12. So for the last few years, that's kind of been where our focus is. And with these workshops that we've been doing for undergraduates, and it turns out there have been some graduate students in them too at places like Bowie State, and sort of this one that had students from a range of places, and the one we're doing for Howard is more at the undergrad plus level. So I feel like maybe shifting back to that a little bit.
And for the K-12 students, what's the most difference of quantum from the AI or robotics? I think the AI and the robotics is very hot in elementary education.
I would say they're not getting to they're not getting to AI, right? They're starting to think about computing, computational thinking, especially at elementary. In high school, maybe a little bit. In sort of late high school, some of the computer science stuff gets to AI. I think when we've talked to those teachers who are doing those kinds of things, it's very much, how do you have sort of an advanced technologies course where this is a piece? I actually think we've had a few teachers really interested in, can we create a quantum computing course for high school? That's great, but I don't think that's actually the answer. I don't think that's actually really where we want to go. I mean, okay, I work a lot with a guy and he doesn't actually say this. He's the one who thinks this is silly, who actually teaches that course at Thomas Jefferson, which is a weird place in and of itself. Fine, for those students who already have it, they get all sorts of things that nobody else does. But for most places and most students, developing a high school level course in quantum probably isn't actually the answer. Is how do we introduce it more broadly, get these ideas, get students thinking about this might be something of interest, and what do I need to pursue it when I get to college? What sort of background? How do I get interested and involved in it? I think it probably makes more sense, like it does for AI, right? They're just getting there. They're not going to get to fully understand how to do that.
I think high school students can do a lot of projects about AI.
In terms of, well, it depends on what you mean about, right? They can learn about, but actually starting to do some of the more fundamental work, programming side of things. I mean, some of them do, some of them get to that point, but getting your average high school student to that computing level is often hard in most schools.